Thanks for having me. My name is Russell Richie. I'm a postdoc at the University of Pennsylvania, working with Sudeep Bhatia. And today I'm going to present some work titled Similarity Judgment Within and Across Categories, a Comprehensive Model Comparison. So everyone here in this audience probably knows that similarity is a very fundamental construct in cognitive science. It seems to underlie a lot of different cognitive phenomena, including categorization, generalization, discrimination, and judgment and decision making. For example, there's a very popular model of categorization called the generalized context model, and that model holds that we categorize an item with a particular category if the item is sufficiently similar to the members of the category. So modeling similarity is thus quite important, I think. And like any cognitive model, to specify a cognitive model of similarity, we're going to need two components, representation and process. We're going to need a representation of two things and then a process that compares those two things. And in the case of similarity modeling, at least, there's different theories of representation that can be combined with different process theories to a large extent. And so testing different such combinations is the goal of our work. And before I delve into specifying different kinds of representations and processes, let me say a little bit more about the kinds of similarity judgments that we are interested in. So first of all, I should make clear that I'm interested in similarity between words, although I do draw some inspiration on from the study of similarity in images, and our work may also have implications for understanding similarity between other kinds of entities. So if you're familiar with the study of similarity in words, there's a number of benchmark data sets of similarity that you might be familiar with. I'll just mention a couple to make clear how our empirical data contrasts with these benchmarks. So one popular benchmark is WordSim 353, where participants are asked to rate the relatedness of a bunch of different word pairs. That contrasts with the data set known as Simlex 999, where participants are told to rate similarity such that near synonyms scored high, but words that were merely related scored low. So the pair coast shore gets a high rating in Simlex 999, where the pair closed closet gets a low rating because they're semantically related, but they're not similar. In contrast, both of these pairs get high ratings in WordSim 353. Another common benchmark is the TOEFL synonyms test, which is just a bunch of multiple choice questions asking a participant to pick the nearest synonym among a set of competitors. And so these data sets have been useful, I think, in developing and testing various lexical representations and similarity functions, but there's a different sort of similarity data that I think is important to consider, and that is similarity among a large set of cohyponyms in some categories. So here I have a set of fruits and ratings of similarity between all the possible pairs of fruits in this category. And I think this sort of data is, in some sense, more challenging than the other similarity benchmarks because it requires distinguishing many different levels of similarity among a set of items that are already generally pretty similar. But this sort of data is also closer to what many cognitive scientists are interested in. For example, this is the kind of data that we would collect if we wanted to do multidimensional scaling and then maybe fit an exemplar model of categorization like the generalized context model. So this is the kind of similarity data that we're going to try to model. And so now we can get back to talking about the different kinds of representations and processes that we will combine. So as most people in this audience probably already know, the most popular representations for modeling similarity among words come from vector space models of semantics, which exploit distributional statistics of words in large bodies of text. And we'll consider a range of different sorts of representations along these lines. Many of you are probably already familiar with Word2Vec and GloVe. So I'll say a little bit more about the other ones. So fast text is a representation that uses the CBOW algorithm, which is a variant of Word2Vec. But the cool thing about fast text is that it also exploits subword information. The upshot of this is that you can generate vectors for new words that are morphologically related to words in the training corpus. These other two GloVe representations that I'm sort of mousing over here are of special interest. I'm going to refer to these as sort of adversarial, post-spec, and paragram. These are both representations that have been specialized to reflect similarity and not merely relatedness. The details of these procedures vary, but basically what happens is you take some pre-trained word vector representations and then use some additional constraints, maybe in the form of pairs of synonyms and antonyms, to move the word vectors around in the space a little bit more to try to better respect similarity relations. And it turns out that those sorts of specialization procedures improve performance on Simlex 999 and performance on various kinds of natural language processing tasks. So we're especially interested to see if these vectors, these specialized vectors, perform well on the kind of similarity among cohyponyms that I mentioned on the last slide. The last pair of representations at the bottom are based on a recent large set of free association norms called the Small World of Words, or SWOW for short. If you're not familiar, in association norms, participants are given a cue word and are asked to think of words that come to mind. That sort of data generates a cue response matrix, where you can use the cue vector as a word embedding or word representation for a word, but you can transform that cue response matrix in various ways to generate more useful representations. Turns out a very useful procedure for transforming the matrix transforms the matrix such that a cue response cell approximates the activation of a response from a cue under a decaying random walk through memory. And that sort of representation also performs very well on Simlex 999. So the first SWOW representation is just these vectors as provided by the authors, but because these are much high dimensional than the other representations I also try reducing these vectors to 300 dimensions through SVD. So that's all the representations we're gonna try out. For similarity processes, we consider a number of functions, most of which will probably be familiar to everyone. Cosine similarities, of course, the standard similarity metric used with vector space models by and large. But to a large extent, there's not a good reason for this other than just precedent and convenience. That's not always true, but I think generally it is. Other functions like city block distance, Euclidean distance, or even Spearman correlation have gone relatively untested despite their a priori plausibility. In addition to these unweighted similarity functions where every dimension of a vector space matters equally, we're also going to consider weighted functions. And the reason we consider weighted functions is that it's possible that the similarity task induces special attention to certain features of the stimuli, which may or may not vary across different categories like fruits or vehicles or sports. A quick note that I haven't explained the last function in this table, augmented city block distance, for the sake of time, but you can ask about it during Q&A if you're curious. So how do we learn the weights? It's pretty straightforward, actually. Suppose we're trying to learn the weighted dot product function. Suppose we have two items like apple and apricot with vector representations that start like this. All we have to do is construct a comparison vector, which is the result of some element-wise operation between the two input vectors. In this case, it's just the element-wise product. And we do that for every pair of words to get a design matrix. And then to learn the weight vector, we can just regress the similarity ratings onto the comparison vectors. Because the comparison vectors are high dimensional, we use regularized regression to avoid overfitting. We'll constrain the weights to be non-negative so that the weights emit a straightforward interpretation of the salience or importance of each dimension. We'll use nested cross-validation to simultaneously find the optimal regularization strength parameter and evaluate models. And we'll assess model fit with the Spearman correlation between the predicted similarity ratings and the actual similarity ratings. And I should mention at this point, this is not a procedure I came up with. Peterson et al. Used this approach to great effectiveness with image similarity and image representations derived from deep neural networks for image classification. And there's some interesting ways in which our results are going to diverge from theirs, which I would love to talk about in Q&A. So a little bit about our empirical data. We constructed 8 categories of 20 to 30 words each. These are largely modified from the Leuven concept database. The categories included vehicles, vegetables, sports, clothing, birds, fruit, professions, and furniture. Participants gave Likert scale ratings of similarity from 1, not at all similar, to 7, extremely similar. Collected 365 subjects on prolific academic, and each subject did just a single category. And the other thing I should mention is that for now, we're not modeling participant level heterogeneity. We're just averaging over participants' judgments so that we have a single rating of similarity for every word pair. So in the next couple slides, I'll show some heat maps of the Spearman correlations for different representation similarity function pairs averaged across all 8 categories. So first, among unweighted similarity functions, we obtained a few key results. So number one, while cosine similarity is tied for the best when we average across representations, it doesn't have a consistent advantage across different representations. For example, it's slightly edged out by Spearman correlation for the glove vector specialized with the adversarial post-specialization method. So you can see Spearman does just a little bit better. And actually, the representation unweighted function pair with the highest performance was the association norms reduced with SVD combined with a Spearman correlation as a similarity function. This pair achieves a correlation which is 0.06 points higher than the correlation achieved with the same representation and cosine similarity. The second thing that emerged from these results is that we found no advantage for the text-based vectors that were specialized for similarity. These do not present any advantages over their unspecialized counterparts. So again, the specialized text-based vectors are this glove vector specialized with the adversarial post-specialization method and the glove vector specialized with this paragram method. And again, this sort of null finding is kind of interesting given that these vectors perform so well in Simlex 999. And we'll return to that issue briefly at the end. And then the last thing is we found that word vectors derived from free association norms may have a small advantage over text-based vectors, at least when they are first reduced with singular value decomposition. Using the similarity judgments to supervise learning of the weights, we can substantially improve the cross-validated performance. The average performance is over 0.2 Spearman correlation points. And the best model, SWOW-RW, so that is the unreduced association norm vectors. The best model, SWOW-RW, with any similarity function except weighted Spearman correlation, achieves a correlation of 0.77. And so another thing to notice here is that the introduction of weights seems to have generally eroded the difference between similarity functions even further. So it's a question how identifiable the different weighted functions are. And I have some pocket slides about this, which I'd be happy to show during Q&A. But the lack of advantage of the specialized vectors over their unspecialized counterparts is still apparent. And now the advantage for association norm vectors is a little bit more consistent, okay? And at this point, I want to emphasize that we're learning separate weighted functions for every category of items like fruit, furniture, and so forth and so on. In other words, when I'm training a regression to learn the weights, I only consider, say, the judgments of similarity between fruits. So it's an open question at this point how context or category specific these weighted functions are. To test that, we tried 2 different things. First, we tried learning a single weight vector for 7 categories and testing the weight vector on an 8th held out category. It turns out that this works no better than using no weights at all, and it's often worse. The other thing we tried was training and testing on all 8 categories simultaneously. This works a little bit better than not using weights at all, but it doesn't seem to work as well as learning separate weights for each category. So to summarize, just one moment, please. Sorry. Where'd my mouse go? So to summarize, we found that text-based vectors specialized performance on Simlex 999 have no advantage over unspecialized counterparts. It's not totally clear why this is the case, but it might be that there are just not enough words in our categories and the lexical constraints that are used to specialize the word vectors. But it's perhaps a little bit puzzling that these specialization technique should hurt performance, except maybe to the extent that the specialization techniques move vectors from positions in space that are already optimal or near optimal for respecting the sort of similarity relations that we were interested in. We also found that association norm-based vectors have small advantages over text-based vectors. Again, it's not entirely clear why this is, but other people have suggested that the superiority of representation from association norms might be due to weaker pragmatic constraints in the generation of free association. So for example, in a free association task, people are free to respond to banana with the word yellow, but in text, so in corpora, they're unlikely to say things like the yellow banana, because that's usually pragmatically felicitous. You don't need to specify the yellow banana. Bananas are by default yellow. And that's a bit of a problem because yellowness is in some sense a fairly salient property of bananas. So that's maybe not going to be reflected quite as well in text. In terms of unweighted similarity functions, we found that cosine does not offer consistent advantages over other functions despite its dominance in vector space applications. And in fact, unweighted Spearman correlation, when paired with the association norms reduced with SVD, yielded the best performance. And I think this is, again, kind of interesting because there aren't that many applications using Spearman correlation as a measure of similarity as far as I know. Next, we showed that it was possible to use human similarity judgments to learn weighted similarity functions, which generally outperform unweighted functions. But we found that learning category general weighted functions was generally pretty hard. And this is consistent with a lot of classic research that similarity is context dependent, which in this case means that the set of items induces a context for similarity judgment, and this context weights certain dimensions more than others. There we go. So there's a number of directions that I think this work could go in the future. First, I very briefly talked about how the weighted similarity functions were hard to distinguish in our data. So it may be useful to use optimal experimental design techniques to select stimulus sets that can identify the weighted functions. Second, I'd like to see the empirical similarity data, the kind of empirical similarity data that we used. I'd like to see that used to guide development of new vector space models, much like Similex 999 and the TOEFL have. And then last, the direction we consider most exciting is further understanding and formalizing the effect of context or category on the weights, such that the weights can be predicted a priori from the items themselves without the need to supervise learning with similarity judgments. And there's a couple classic effects in, or principles in cognitive psychology that may help predict the weights in this way. The extension effect, for example, finds that features influence similarity more when they vary in the entire set of stimuli, while the size principle actually says something rather different, which is that weight on a feature is inversely proportional to the number of items possessing a feature in a given context. So testing these kinds of principles, I think, is a clear direction for future research, and it may also be that explaining the context dependence of weights in lexical similarity judgment will require the development of entirely new principles and theories. And with that, I'd like to thank you all. We have a preprint at SciArchive that you can check out if you want. All of our data is hosted at OSF, and I'd like to thank members of my lab pictured here and attendees of Psychonomics and funders. And that's it. Thank you so much.